Electromagnetic interference, or EMI for short, describes the radio frequency disturbance generated by electrical circuits. There are various EM compatibility regulations to limit the amount of parasitic emissions, to prevent devices from perturbing each other. EM compliance is usually checked in a testing facility with broadband antennas in the far field. The emissions are then compared to a reference curve. This is a typical test setup. The issue here is that it is time-consuming, very expensive, and it does not give a good insight for the circuit designer. Hence, I wrote some Python code to make fast maps of the near-field EMI with cheap material. I came up with two methods. The first method I researched uses a 3D printer to perform the scans. The idea is to move an H-field probe using the carriage of a 3D printer, my Skeleton 3D in this case. The probe is homemade, mounted on a 3D printed holder. This probe could be replaced or coupled with an E-field probe. The Python script controls the printer by sending G-code. It simultaneously measures the EM field with the RTL SDR radio receiver. This clip shows the printer performing a fine scan, where the grid resolution is 5 mm and the grid size is 85 mm square. Frequency span is 2.6 MHz, and this takes about a minute to complete. There are 4 parameters that affect the speed of the scan: the size of the zone to map, the resolution of the grid, which is also limited by the size of the H-field probe loop, the frequency span of the scan. For instance, 1 gig would take a much longer integration time, and the feed rate, which we can change. This printer type is very convenient for this purpose, compared to the iFreestyle for instance, because the bed and board under test doesn't move, only the probe does. With this method, this is the kind of result we can expect. It gives a very good view of the spatial distribution of near-field emissions. We can do broadband scans even with a narrow receiver by sweeping the center frequency. However, the main issue here is that it is not very practical, requiring a 3D printer, mounting the probe, etc. The second method I explored is by using a camera and machine vision to track the position of the probe in real time. So, this is how it works. The probe is manually scanned across the board. The RTL SDR measures the RF emissions. A camera tracks the position of the probe over the board. The script uses the data to generate the map. Similar to before, the output is a 2D heat map. This is my scanning setup. Now actually performing an EM mapping of an Arduino Uno board with this technique. The big advantage of this method is that it is ridiculously fast to get pretty high resolution scans of boards, or even specific areas. Additionally, because the measurements are done live, we could dynamically adjust things. However, compared to the previous method, the huge drawback is the lack of repeatability. Because the power measurements follow an inverse square law to the distance, a slight shift of the position of the probe may greatly affect a measurement. This could be improved with a board-specific jig, but it won't be as good as the first method. Still, the ease of use and speed makes it an idea worth exploiting. Some smarter machine vision code might be able to compensate the variation in the positioning of the probe. A write-up article of this video is on my website, links are in the description. Also in the description, is a GitHub repository containing all the code to run both methods.